Wow, yeah.
So, hi everybody. So I am Nicolo Piccione, and this is the title is Fundamental Mechanisms of Autonomous Measurements for Non-conserved Quantities and Saturation of Fundamental Laws, which I know it's very long, but the fact is that I am going to talk about different things, and I just merged the two titles to make this title. So that's why it's so long. Yeah. Anyway. Okay. Okay, so so this is a work that I've been doing in the Templeton project. So it's me, Maria, Patrice, which is not here, and but also Kater and Andrew, and of course Alexia. Okay, so this is the outline of what I'm going to talk about. And I will make a brief introduction in which I will say, I think for the fourth time this day, that if you measure something that is not energy, you can change the energy of the system. Then I think I will talk for the fourth time this day that there is something called pre-measurement. But for the first time this day, there is something here, it's called wave theorem. Oh, and this is just the introduction, and I will talk about this in conjunction, I mean, specifically to what is useful for what I'm going to talk about, so not wave theorem in general. And then I will talk about these two works that are both, let's say, in the end of their process. So we are actually writing the papers on these things. Okay, so one is simple setup in the waveguide, as we talked already many times today, in which we use a pulse to measure a qubit in the sigma z direction. But the twist is that the qubit Hamiltonian is tilted. So the qubit Hamiltonian will not be sigma z, but will be something tilted in the Bloch sphere. And then we will use the same kind of measurement, but this time in an even simpler setup with a one photon pulse instead of a coherent pulse. And in this case, we will show that we can saturate something called Ozawa's bound, which I will tell you what is it. And then we generalize a bit also this by studying optimal discrimination and reversibility. Okay, so that was the preview, the trailer of my talk. So this is something that we know very well now, but I repeat it. So in this example, assume that the Hamiltonian of my qubit is not along sigma z, but is along sigma x. And then I do a measurement of sigma z. So what happens if I start from this state is that if I don't read the measurement, I would go to this state in the z-axis of the Bloch sphere. But if I look at the sigma x-axis, I see that its coordinate changed. So this means that the energy of the qubit changed. And this is just to convince you, you are already convinced, but anyway, that if you measure something that is not commuting with the energy of the system, you can actually change the energy of this system. So with respect to what people have taught today, instead of tilting the measurement, I'm tilting the Hamiltonian, but it's basically the same thing. Okay, so and in this talk, we are going to actually focus on the pre-measurement. So that's why there is this question. Does this energy change have effect on what performs the measurement? So we will see if we can actually see the effect of this energy change on the meter when we analyze the pre-measurement. So the pre-measurement, I have it here, a slide on the pre-measurement. So the pre-measurement is also, in some sense, the first ring of the von Neumann chain that has already been cited sometimes this day. So the von Neumann chain is the following idea. You have a system, this system interacts with another system, and then this other system interacts with another system, and so on and so forth. So you create a chain of correlations, but at some point, one of these systems is macroscopic. So it cannot be in a superposition. And therefore, you get the collapse, and cascade, you have also the collapse of the system you are measuring. But if you just focus on the first chain, this is what happens. You have a system, you have a meter, you put them together so that they interact, and then you separate them, and then you want to measure the meter, and from the measurement of the meter, infer what was the state of the system. In the ideal case, this works as follows. I start from a so-called ready state of the meter, and if the cube, I will work with qubits, so I would just use examples with two-level systems. If I start from the ground state, I will get a certain state, G for the meter, and if I start from the excited state, yes, this is psi E, this is a typo. You will get an excited state for the meter. These two states are orthogonal, and therefore I can measure the meter and infer what is the state of the qubit. So, okay. So a long time ago, Wigner had the same idea. And he studied a system similar to this one, in which there is a system and a meter. And what is showed is that if you take all these assumptions, so you have an observable for the system that you want to measure, an observable for the meter that you use to infer what was the value of the observable on the system. You use a certain, you say my dynamics, I call it U. I have the two Hamiltonians of the system, and this is some sort of scattering dynamics. So what happens is that at the end, total energy is conserved. So if the observable of the meter doesn't commute with the, the observable of the system doesn't commute with the energy of the system, this ideal pre-measurement that I showed before is not possible, mathematically speaking. You cannot have it. However, he also showed that with an example. If the energy dispersion in the meter is high, you can practically have an ideal pre-measurement. So with a classical measurement, this is not a problem because your meter is macroscopic. And so usually has an energy dispersion which is many orders of magnitude bigger than the system you're measuring. So it's not a problem, but it can be if the meter is quantum as the system. Okay, so this is important because we will basically see this wave theorem in action in our example. Okay, so what's the idea? We are in a waveguide setup as Maria before. We send a pulse that in particular will be usually a coherent pulse. This interacts dispersively with our two-level system. And in the ideal case, we have this mapping and we have this. So this is basically the ideal pre-measurement as I explained in the slide before. However, with respect to the usual case, now the Hamiltonian on our qubit is tilted in this way. So theta, when theta is 0, the qubit is as the usual Hamiltonian project, which is aligned with sigma z. And then theta can increase up to pi over 2 and being aligned over the x-axis of the Bloch sphere. Okay, so now I introduce some notation just to understand the following slide. So we have the tilted qubit Hamiltonian. The pulse has a duration, a temporal duration. So it's the amount of time that it will basically interact with the qubit. And we call this sigma t. And then we have a parameter called t0. T0 is when the center of the pulse is on the position of the qubit. Yes, I recall here that for a Gaussian pulse, we have this relation because they are of minimum uncertainty. And the last parameter is this parameter phi, which can be understood again in the ideal setting. So in the ideal setting, this phi is the separation in phase space between the two output states of the meter. One, if the qubit is excited, and one, if the qubit was in the ground state. So if phi is 0, these two things are equal and I'm not doing a measurement. If phi is pi, these two things are maximally distant. And if my pulse has enough photon, this is basically a perfect measurement. Okay, so and now I will show you first. I will do something strange here. So in the paper, I'm going to write first I analyze the dynamics and I solve the dynamics and explain everything. And then I will show the plots. But here I show first the plots because it's more cinematic, let's say. like you put the cliffhanger, you cut and okay. So anyway, so this is the result for a coherent pulse with 4 photons, and this is the result of a numerical simulation done starting from the collision model approach. So on the left, these 9 plots are the phase, the imaginary part of A of t. So with respect to the previous slides, they are the result time of this, of the y coordinate on this phase space plane. And basically, this is the how to say, indication of a good measurement if it has this form. Because when starting from the other state, so here we're starting from G, if you start from E, this will be upside down. And so you can easily distinguish between the 2 cases.
Sorry, the x-axis is time here, is that right?
Yes, I forgot the theorem T0, but yes, the x-axis is time in both left and right. Okay, and we have in the column, we have the increasing interaction, while in the row, we have an increasing tilt of the qubit. And then we have a short pulse, a pulse of medium length, and a very long pulse. So as you can see, what happens when you go to long pulses is that the measurement is not useful anymore. Basically, you cannot, if you put this upside down and you start to try to understand the phase, you are going to have a very difficult time to do this. This can be understood in the following way, which is that if the pulse is very long, the qubit is evolving while it is interacting with the pulse. And this can be seen in the plots on the right, where we have the qubit dynamics with the 3 block components. So it is evolving on the time, and basically the pulse is, it's like saying, okay, but what am I measuring exactly? Like, well, while I'm interacting, the qubit has done so many oscillations that it's not even clear what is the state of the qubit that I'm measuring anymore. Okay, so, and you can see this from ear to ear. So in general, we can see this from these plots, that the higher is the tilt, the worse the measurement gets, and this is clear from the medium and the long pulses. And that the longer the pulse, the worse is this phase measurement that we are doing. Okay, and this is in accordance with the Wave theorem, because a long pulse is very sharp in energy. So as we saw before, you needed a meter which had a big dispersion in energy to have a good measurement. So these short pulses do not have a big dispersion in energy because they are very long in time. And so that's why we don't have a good measurement. So the Wave theorem is in some sense verified by these simulations. Anyway, now the question was, we can see the effect of this on the meter. So what we did is now to compute the spectra, the output spectra of this pulse of light. And we can see that the only situation in which we can actually see a spectral deformation are these situations here, in which we have also a bad measurement. So all these plots strongly suggest that you cannot have a good measurement and also a very visible effect of this measurement on the energy of the meter. So you have a good measurement when this interaction has basically no effect on the meter that is performing this measurement. These plots are done for starting from GZ or GX. It's the same conclusion.
Sorry, pause a second.
Yes.
So in this case, so we're looking at different values of theta. So this is not initializing the eigentheta of the qubit, it's Hamiltonian. So there's some dynamics even when you're not measuring something going to
Yes.
Is that also the case in the previous slide?
In the previous slides, when
you described it as undergoing.
Yeah, the qubit
so
is
undergoing some.
Yes, the qubit is doing many oscillations, especially when the pulse is long, because these plots are from t over t0 from 0 to 2.
He is asking where is the state we are starting from?
But yeah, so it's not an eigenstate
No.
No, it's not an
of the
eigenstate.
qubit Hamiltonian
No.
or of the measurement Hamiltonian. So you'd have a competition between dynamics and measurement.
Mhm.
I'm just trying.
Yeah, no, it's the initial state. I also have the plots when starting from, for example, if I have the maximal tilt, I start from Gx. And I mean, I didn't want to, to put all the plots that I've done in the presentation, but what happens is that you start from a straight line, and then when you start the interaction, it starts oscillating more and more depending how long is the pulse and how strong is the interaction. So this effect of oscillations is you have it even if you start from an eigenstate of the Hamiltonian. It's just that it starts during the interaction.
Because when you say state of the Hamiltonian, it means state of the bare Hamiltonian.
Yes.
Of the
Of the qubit.
So the
part.
tilt and the
tilted Hamiltonian.
Yeah.
Let's
Yes.
say theta is equal to pi over 2 or
Yeah.
whatever, and then you start in Hamiltonians in the X eigenstate.
yes.
Now the measurement's going to induce some sort of dynamics, and
Yes.
eventually you'll get oscillations or some sort of.
Yeah,
Mhm.
because the
Yeah, you start from a qubit which is stationary because it's an eigenstate, but then as long as you start the interaction, it starts also oscillating.
Fair. And then you say it's a bad measurement because the qubit is undergoing dynamics during the measurement, or what
Yes.
makes you say it's
Yeah.
a bad measurement?
Because you have this phase that becomes positive and negative all
I
the
mean,
time.
two things. One is what you said also, because the qubit is undergoing a dynamics during the measurement. So you can infer what was his state before, but you can't, it's not
So-
repeatable somehow because it changes during the measurement. And then also the fact, really the amount of information that we can extract, because here the pointer observable somehow that you're looking at to know what was the state is this phase that it takes. Because the coupling is a dispersive coupling. So it's
So it's a bad measurement because it's not projecting into one of the.
exactly. It doesn't flip clearly the phase. So when you do the measurement, you
Yeah.
are right.
So the reason why these plots are made starting from GZ is because in the ideal measurement, when you start from GZ, you get this curve. And when you start from EZ, you get the curve upside down. And so you can, when you then integrate the phase, so you get a value and another value, and they are very different. And therefore you can discriminate between these two states. But as you can see, for example, here, when the pulse is long, this thing oscillates a lot. So when you do the integration of the phase, etc., you get something that is like 0, both in the G and E cases. So they are almost indistinguishable with this phase measurement.
So it seems to me that when the pulse width is small, the sigma z is almost -1 for all the cases. But
When the pulse is short, yes, sigma z, you start from GZ, and you have that sigma z is almost it's like -1 over the entire dynamics, because when the pulse is short, this time from 0 to 2t0 is a very short time with respect to the proper time of the qubit. So the qubit doesn't have time to evolve. And therefore, you're right, sigma z has the same value along all the dynamics. And that's also a reason why you get the good measurement. Okay. So then I was talking about the spectra, but there was a final thing to say. These spectra, as you can see, whenever they have deformation by forming this structure with 3 peaks. So now the point that we were trying to do is, okay, but why these 3 peaks? So to explain why this output spectra have 3 peaks, we now talk about the dynamics of this system very rapidly. So the idea is the following. We have a dispersive interaction between the pulse and the qubit. And dispersive means that there is a conservation of the photon number. So in this interaction, photons are not created and are not destroyed. which means that I can study the dynamics of this entire thing for each number of photons subspace. So I can study the dynamics in the vacuum, I can study the dynamics in the 1 photon subspace, in the 2 photon subspaces, in the 3 photon subspaces, etc. And we actually derived the formal solution to all of this, which I didn't report because it's a thing with temporal orderings, and I mean, it's not things so easy to grasp, but we can make this discussion anyway. The output state, for example, let's say with 1 photon, is formed by many wave functions of the field. In particular, there will be a wave function in which you start from the ground state and the qubit flipped in its bare Hamiltonian. And another wave function in which you start from the ground state and the qubit didn't flip. And the same if you start from the excited state. And you can do the same reasoning for any number of photons. So for example, with 2 photons, you can have ground, flip, flip, ground, flip, not flip, ground, not flip, flip, ground, no, no, etc. Okay, so here, for example, this is the output spectrum. When we start from the ground and we have a jump, we start from the excited and we have a jump, or we start with the input, which has the same output of ground, no jump, and excited, no jump, because obviously, if the qubit doesn't jump, it never jumps, the output spectrum is going to be exactly the same as the input. And we can see here that in the case we start from the ground, with a jump, the qubit has to absorb energy from the field. So what happens to the spectrum of the field is that it shifts completely to the left. If instead we start from the excited one and we have a jump, the qubit gives energy to the field, and therefore we have the spectrum that the blue shifts, basically. So now, what is the intuition about what happens in the case of the photon, of the coherent state? That this happens for every photon in the pulse. So for example, when I study the 3 photon subspace, I will have each of the 3 photons undergoing something like this, in which you can have a shift toward the right of omega q, or a shift toward the left of omega q, and therefore combining all of this together, you will also have you will always have peaks in these 3 positions: 0, minus omega q, and plus omega q. Okay, so now we want to back up this intuition. So what we did is that we computed numerically the spectrum of all the output field states from 1 to 3 photons. And this is in the next slide. So we have the 2 photons here and the 3 photons here. So in the 2 photons, we have these states, which you can read now because you know jump, ground, no jump, jump, ground, jump, no jump. So this is the legend. And this is for the 3 photons, in which I always start from the ground state because otherwise it would be a mess. And if you start from the excited state, you just have to mirror with respect to the 0, and you will get the same thing. So what is the idea? The final wave function in the output will be composed of these wave functions with different weights depending on the interaction, the tilt of the qubit, and other things. But these wave functions are always the same, independently of the strength of the interaction or the tilt of the qubit. So if these wave functions have always 3 peaks, also the combination of them and the interferences of them, etc., will have 3 peaks. And this is what we observe in the case of 3 photons. All the wave functions have 3 peaks. One interesting thing is that it also matters when the jump occurs. So for example, here you see that node NJN doesn't have the same spectrum of J and N or N and J. So having a flip of the qubit when there is the interaction with the second photon of the pulse leads to a different spectrum that when the qubit flips because of the first or the third interaction. So, I mean, I don't know exactly why this is so, but I thought it was interesting to point out. Okay. So to resume for this first part, we know that we have seen that the measurement is well performed for short pulses, but the spectral deformation on the meter is difficult to see. On the other side, if the measure for long pulses, we have a measurement that is badly performed, but the spectral deformation is clearly visible. And then we showed that we can actually analyze the dynamics. By the way, the dynamics is resolved in time. So we don't only have the scattering states, we have the states, formally speaking, at all times. And we basically explained why, when the pulse is long, we have this structure with 3 peaks in minus omega q, 0, and plus omega q. So this is the recap of this first part. Okay. So now I go on to the other thing, which is connected. But so Ozawa's bound. So I put here a reminder with the notation from the slides on the wave theorem, and I speak a bit about this Ozawa's bound. So what Ozawa did in this paper is that he defined this noise operator, in which you can see you have the observable of the system, which is computed on the initial state, and then the observable of the meter, which is computed in the final state, and the difference between these two observables. He defines this error, in which he basically computes the average of the square of this operator. And this is 0 if your measurement is ideal. So if you can discriminate perfectly which was the state of the qubit at t equals 0. And finally, he assumes this thing called Yanase's condition. Yanase was the third name in wave theorem, Wigner-Araki-Yanase. So what this condition means practically is that after you have done your remeasurement, it doesn't matter when you do your classical readout on the meter, you can always use the same observable to make this inference to understand what was the state of the qubit. So it's basically a condition of, I would say, practicality of the measurement. So assuming all of this, Ozawa's derived the bound, which is this one. So the error on the state psi s is always higher than the bound on the state psi s, which has this form. And it depends on the commutator between the observable you want to measure and the Hamiltonian of the system, on the initial state, and on the energy dispersions of the system and the meter. So here we basically recover, in some sense, what Wigner derived not analytically, in some sense. So the idea that when the energy of the meter goes to infinity, it becomes very large, this bound becomes basically 0. And therefore you can actually have a perfect discrimination and also a perfect measurement. Okay, so we now analyzed something very similar to the previous case, so the previous system. But this time, instead of sending a coherent pulse, we send one photon pulse. This one photon pulse goes through a beam splitter, which is a balanced beam splitter, so 50-50. There is a part which interacts with the qubit and goes through, and another part which is phase shifted by always the same amount. Then they recombine here with another beam splitter. And the idea in the ideal measurement is that if the qubit was in G of Z, the two paths recombine to go in this way to this photodetector. While if the qubit was in E of Z, the two paths recombines here, so they go in this photodetector. So then you have the measurement in this photodetector, and you know which is, or which was, better to say, the state of the qubit. And this obviously satisfies Yanase's condition, because after the measurement, you have just to measure if there is a photon here or here. So this thing doesn't evolve in time. So it commutes with the Hamiltonian of the field, and therefore satisfies Yanase's condition. Okay, so now the trick is the same. We tilt the Hamiltonian of the qubit, we study the dynamics, and we compute the Ozawa's bound and the error. And we find something interesting. First is the Zalo's bound become this formula, which is completely independent of the initial state of the qubit. So it's always the same, independently of what was the state of the qubit. And the same is for the error. So the actual error, you get this formula. And this formula is also independent of the initial state of the qubit. So instead of doing what people do in a lot of papers in which you have to maximize over all the states, etc., you don't need to do that, because the error is always the same. So it's very clear what this error means. And yeah, here I just remember what phi is. It's the same as previous in the previous slide. So it's the phase acquired by the pulse. Okay. So now we say, okay, let's put ourselves in the condition in which we are doing a good measurement. Okay. So when we are doing a good measurement, we are using a short pulse because that's what we know. So if the pulse is short, it holds also this because again of the minimum of the uncertainty principle, and we can expand to first order both the bound and the error. So this overlap, I forgot to say, this is the overlap. Sorry, I forgot. This thing is the overlap between the input pulse and the output pulse when it's shifted by the interaction with the qubit. Because the qubit is tilted, so as we saw before, the output spectrum is blue or red shifted. And here I am analyzing the case in which is blue shifted. Okay, so anyway, when you do this, this perturbation in the regime of short pulse, this thing becomes this. And basically you get that the bound gets this form and the error gets this form. And these two formulas are equal only if the pulse is of minimum uncertainty. And the pulse of minimum uncertainty is a Gaussian. So basically, we have shown that you can saturate the bound caused by Zalo. And that to do that, it is actually necessary to use a Gaussian pulse, which I don't think it's intuitive to say, it has to be a Gaussian. So I am happy with this result. Okay. Okay, so lastly, we said, okay, but what if you go back? You say, I don't want to do the measure with the detectors. I want to do the optimal measurement that I can do after this second beam splitter. So in this case, to calculate your ability to discriminate what was the state of the qubit at t equals 0, you can use this thing called precision. So first of all, I point out that when you do this kind of maximization, you are automatically abandoning Yanase's condition, in the sense that when you do this calculation with the fidelity is basically finding you the best classical measurement that you could do on your meter. And therefore, it's very possible that this best classical measurement is not of this kind, doesn't respect Yanase's condition. So what is this thing? It's one minus the fidelity between these two states of the meter. This is the final state of the meter when the qubit was in the excited state at the beginning. And this is the final state of the meter when the qubit was in the ground state of sigma z at t equals 0. So this computation we did, it's you have to use some tricks to do this computation, but in the end it's doable. And you obtain this plot here, in which we can see something, how to say, very counterintuitive, I would say. First, in this set, in which we have the maximal interaction and maximal tilt, we can have perfect discrimination even for very long pulses. Second thing is that for some reason, when you go to long pulses, you can even increase your ability to discriminate between these two states of the qubit. So, and all of this depends on the fact that you are abandoning Yanase's condition and you are optimizing over all possible classical measurements, which also means that in practice, the classical measurement doing this is possibly something incredibly complex to do experimentally. However, one says, okay, but if I can get this perfect even for long pulses, which means that they are very sharp in energy, doesn't this go against the wave theorem that we saw at the beginning? And the answer is no, because as Maria was pointing out before, there is another thing in the ideal measurement, which is the repeatability of the measurement, which is I get a result, then I do the same measurement, I should get the same result. This is not the case, as you can see in this other plot that we did, in which we used a thing that for the moment we call the reversibility, which is a slight generalization of repeatability. And it works as follows. We say, this is the initial state, this is the final state of the system, so of the qubit, and then you can use any unitary to bring this state back the closest possible to the original one. So why we added this thing of the unitaries? Because, for example, if you start from the ground state, you do your measurement and it goes to the excited state, and you know that when you measure G, you made the flip, it's easy to apply another unitary to just flip the qubit back again. So I would count that as a repeatable measurement in practice. And therefore we define this thing called the reversibility of the measurement. So this is the definition, but then you can show that this is equal to the maximum eigenvalue of the final density matrix. And this is what you get by plotting this reversibility, which has a minimum value of 0.5, because that would be the maximally mixed state of the qubit. So as you can see, when you use long pulses, you never have perfect reversibility. So again, we basically are in agreement with the wave theorem, because even though we have perfect discrimination in some cases, this green line here goes like this in the reversibility. So you have perfect discrimination, but you don't have reversibility of the measurement. So everything goes. What is the case in which you have the perfect measurement is again for short pulses, because you have here perfect reversibility and perfect discrimination. So as previewed by the original paper by Wigner.
What is the green line is defined by this capital theta equals pi?
Yes.
What does that mean?
Theta is the tilt of the qubit. If you remember the Hamiltonian here, theta quantifies how much the Hamiltonian of the qubit is tilted with respect to the z-axis of the block sphere.
Okay. So this one, we have sigma x as the Hamiltonian?
Yes, when you have theta equal pi over 2, basically the Hamiltonian is sigma x.
And
It's maximal tilt.
is there any assumptions on there's no assumptions on the initial state of
No,
the measured qubit. Right.
The initial state here is it's here. You suppose you do the calculations at t equals 0. You can have either E of z, so the qubit is in the excited state of sigma z, or in the ground state of sigma z, and then you quantify your ability to discriminate the two output states of the field based on what was the state of the qubit at t equals 0. Okay, so okay, to recap this second part, we showed a simple interferometric setup in which we can basically saturate this Ozawa's bound with 1 photon pulses. We showed that the saturation, you need Gaussian pulses to have this saturation of the Ozawa's bound. And we also studied optimal discrimination, showing that it is always possible, but at the cost of reversibility of the measurement, as expected by wave theorem. Okay, so that's the end. Thank you. I don't know. Yes.
Yeah, can you please explain again what pi was?
Pi, yes.
How you are setting?
So pi here is, if you send a coherent pulse, is basically this angle that is formed in phase space. When you send a a one photon pulse is the phase that it acquires here when interacting with the qubit. So if pi is equal to pi, which is the best measurement, you get this thing. The phase is I to the plus or minus I pi over 2. But if phi is something between 0 and pi, you get plus or minus phi over 2 here in this space. So in some sense, phi quantifies the strength of the interaction between the photon and the qubit. If phi is equal to 0, there is no interaction, so you'll get no measurement. If phi is pi, it's the maximum. Going over there makes no sense. You just degrade the measurement.
Yeah, good follow-up. Can you show the plots of the calligraphic P?
Yes.
So I see that it's like between 1/3 pi and pi, there's an intermediate value where it seems to be separated most. Is that what am I understanding it correctly?
I don't understand, sir.
So this plot is showing the separability of the states as functions of plot width. Sorry, the pulse width, right?
The pulse length. Yes.
Okay. So if I'm looking at the plots for phi equals to 1/3 pi and compare it to the other ones, it seems like the separation is more in the one for the 2/3 pi, or is that not the case?
So these are the lines for 1/3 pi, right? And these are the lines for 2/3. So when you go from this to this, your precision increases a lot. What is maybe counterintuitive is that you can get some better results with 2/3 with respect to 3/3 for long pulses. Like when you see this green line is over the red and blue line. So this maybe this is not, I wasn't expecting this. But we checked twice this calculation.
Is this for just a single photon?
Yes,
Oh,
this is
different bandwidth.
This is a single photon, which this is a
Varying the bandwidth.
Varying the bandwidth.
Very
yes.
Since you say that your labels are oscillating, right? Does it have to do something with the noise that you're seeing? Because you saw in one of the plots you're saying that labels are oscillating, right? When you increase the length of the pulse.
You mean
In the first section.
in the first section, yeah.
Yes. So because the phase noise depends on how stable is your level, right? So does it have to do something with like how noisy your, when you calculate the phase, when you calculate whatever you're measuring, how noisy your data depends on that one in a way. And does it have to do something with the phase noise or?
So in the first part, we saw that when you have a long pulse, the qubit makes many oscillations, and therefore the phase measurement becomes more and more worse, right? But here, the measurement that is done is not a phase measurement. It's something else that we don't even know what it is because it's calculated with the fidelity. So it's this optimal measurement, but we don't know what this optimal measurement is in practice. What we know from this calculation is that it behaves in a completely different way with respect to the measurement, the interferometric one we did for calculating Ozawa's bound, and the phase one we did.
Because I'm trying to compare it with something really different, because if you have like a qubit and the qubit level is oscillating, then you have a huge phase noise, right?
Yeah, yeah.
So,
Yeah, but
And in the end, what you expect is, of course, that the most it oscillates, the most the phase oscillates,
Yes.
but you are incapable, unable to extract any information because
Exactly.
the coverage is on zero and you can't distinguish the initial state, which indeed is the case. The plots that Nicolo showed is. But this is when you respect this Yanase condition because you are like somehow using the phase as pointer, as the degree of freedom you look at.
Yeah.
And instead, this result is just somehow for us is something which is just interesting because it's a bit counterintuitive. It's saying like, you know, if you relax here,
Yes.
so it's not anymore the phase that you look at. But you only look
Something
at the fidelity, so this mathematical object, which is just measuring how different are the density matrix in their totality. So it's not anymore only the coherence or the population that matters, but it's combination of the two in a way which is then at that point you find yes. But then of course this is like having a good fidelity. If you don't know what to observe, it's
it's
so it's still nothing to measure, but so
Yeah, I mean, the fact that in theory there exists a measurement capable of doing this doesn't mean that we are able to do it. And even if we can write it mathematically, most probably is not something that can be practically done.
no.
So do you guys not know the kind of what the qubit state looks like when we perform this optimal description?
No, we know the qubit state. We use it.
You know it used to be, or you know what it is.
The qubits.
I feel like you know what the qubit state was at t equals 0.
We know
We're
what
just saying here that the qubit state at t equals at the end of the measurement is.
Yeah, so we know we decide what was the state at t equals 0, and then, for example, we use the final qubit state to calculate this reversibility. So we know we have the formula for the final qubit state, but that is not what you have to use to do the measurement. The actual classical measurement that you have to do here is on the meter, not on the qubit. So and this state here instead. I mean, we know it. It's a state that we can you can write by tracing over the qubit. It's quite a complicated state, but yeah, we can calculate it.
But it's not repeatable because why? Because
It's not repeatable.
because it's mixed, or because the final state when you started in ground is, you know, somewhat parallel to the final state when you started in ground.
Because when you start from the ground, in the end you get something which is a mixed state. So you cannot, for example, use a pulse to revert it like freely to the original state.
Yes, this plot reversibility or repeatability, I mean, it's like a concept. So how the final state is similar to the initial one, deals with the state of the target, of the cube.
Yeah.
So this we are talking about the state of target. The other one, the fidelity, the one that Nicolo showed before, this P figure of merit, deals with the state of the meter.
Yeah.
So the one of the field, which should come, we have an analytical expression, it's something, but then the thing is, this something contains any information, not only the phase, other things like how the intensity is changed, I don't know. And
Yeah, I mean, it's a complicated function, the output one.
But did you try something that violates I forgot the name of the guy?
Wait here.
Yeah, no,
I was bound.
yeah, something simple that violates that.
no,
So we do not violate Zawa's bound because when we do this calculation with precision and reversibility, we are not respecting Yanase's condition.
The condition that condition.
Yeah, that is violated, that condition. So you are not violating the theorem because you are not respecting its hypothesis.
this is the point. What we did with the Zawa was saturating it, which is already like interesting because Nicolo showed like when you put a Gaussian field of the right direction, you can saturate, so you can achieve a measurement that's the best that it can.
One more question, just to. So when you see this frequency shift,
Okay.
if the frequency shift is resolvable, that puts you in the regime of a bad measurement with respect to the wave theorem.
Yes.
What is it? What is it about resolving the resolvability of the frequency shift that.
Yeah,
is-
maybe we can
Like
look at.
here, it makes sense that you have like dynamics that are taking place during the measurement scrambles the state. I don't know if you can put it in simple words, why,
The question is why you get this when the measurement
so maybe
is.
when you resolve a frequency shift that goes hand in hand with there being qubit dynamics taking place during the measurement.
Yes.
And that's means you're not in the regime of a projective measurement that's leading into eigenstates. I just trying to restate. That
Okay. Okay.
and you know, I think I understand.
Okay.
There are no more questions. Let's thank Nicolo one more time. So now we have an hour and a half